Okay, good. Yeah, and for the rest of this talk, I will always use the same color bar, which means that yellow is high population density and purple is low population density. And I will quickly try to get rid of this bar at the bottom. Ah, okay, it disappeared, perfect. So let me quickly introduce you to the Democratic Republic of Congo, short DRC. So this is one of the largest countries in Africa, and it's actually super large that for us Europeans, we sometimes get like the totally wrong sense of how large it is. It actually spans from Copenhagen all the way to Sicily. So it's pretty large. Now, the DRC has some census regions or administrative regions, and there are 189 of it. And for each census region, we only get the total count of people that live there. So it's not a lot of information. So on average, every 20,000 square kilometers, we have one number of how many people live there, but we don't know where they're exactly distributed. You can compare this to what we have in Switzerland. In Switzerland, we have the hectare raster. So it's really a huge scale difference. Now, the idea now is to have this low resolution population data and basically super resolve it into a high resolution population map. And then also at the same time, increase the utility of the data that we have. Now, how is this exactly done? We rely on quite a stack of geodata. So those are some variables that have some sort of relation to population. And they are all off the shelf available and open source. So this data can be like distance to road, elevation maps, night lights, and so on. Then also crucially, there is the building counts in it. And this comes from the Google data set. There's the Google Open Buildings data set, it has been released like 2 years ago, and it covers like about 80% of Africa with all the buildings in it. And maybe unsurprisingly, this was also the most important variable for us. So now I quickly want to give you an introduction on how population mapping usually is done, like in the classic literature. So there are different stages on what you do. Usually you have some sort of data, which is level 1, like the census data that I already explained before. And then the first step is to artificially coarsen this census data to a level 0 data. And then on this level 0 data, you basically try to train a machine learning model. This is you have to think about it. It's like a tabular setting with some covariates and population. Then you train a random forest, and then you do inference on the grid level. And the third step is then that you aggregate those grid level predictions to your original census again to validate your approach. This is that. Now, I see 2 problems with this approach. The first obvious one is the evaluation. With this setting, at no point you can validate the grid level because you don't have the ground truth for it. So this is just a very unsatisfying truth, and there is not a lot that you can do about it. But there is one other thing that bugs me a bit, and it is that all those covariates that I just talked before, you first need to aggregate those covariates to level 0, basically doing some average pooling, max pooling operation or whatever to create your training data. But then inference you do not on the aggregated features, but like on the pixel features. So this means you have quite a domain shift between your training data and your inference data. So this is basically the problem that I saw, and I then tried to address. Now, in the setting of guided super resolution, so basically what I thought then is, this problem that we have at hand, it's a guided super resolution problem, because we have a low resolution sensor, the population, we have the high resolution variables, and we want to fuse them together to a high resolution population. And this is like if you put it next to other guided super resolution settings, it becomes quite obvious that it's the same problem. But unfortunately, like if you check the population mapping literature, this is something that nobody has done before. So I went to the literature of guided super resolution, and I came up with my own algorithm for it. And this is called POMELO. So it stands for population mapping by estimating local occupancy rates. It goes like follows. So you start with the covariates that I described, and you want to map them to a population density. So it's really a map-to-map translation with a neural network. Now, the problem is that this population density, the high resolution population density, you cannot supervise because you don't have the ground truth for it. So what we do instead is that we have this sum over census regions such that we create a predicted census, and this predicted census we can compare to the ground truth census. And this gives us some loss signal where we can train the neural network at the end. Now you may ask you may wonder that this is a super ill-posed setting. There might be multiple population maps that would achieve a perfect loss, and this is really the main problem with this setting. So we had to integrate a lot of inductive biases. So the first inductive bias, and also the most important one, was that the building count variables, it's not just any other variable, but we use it in a way that the neural network, it predicts some sort of building occupancy rate, and this occupancy rate you multiply with the number of buildings in this pixel. And then you get the population density out of it. It sounds a bit like a change of variable hack. It sounds very small, but actually if you do this, you reduce the error by like 30%. So it's really significant. One speciality also is that this neural network here, it's quite small. It also has only 3 layers as shown here, and it doesn't have any convolutions. So we noticed that for several reasons, convolutions in these settings is bad. First of all is that the covariates that we use, they don't contain a lot of textures. Like for example, distance to road, it's mostly just like a monotonic function, basically, right? So you don't gain a lot. Also, if you introduce a 3x3 kernel instead of a 1x1 kernel, you just blow up your number of parameters by like factor 9. And if you only have like a few samples, as I showed before, like in Congo, you have the 189 samples, you cannot afford that many parameters. Then the other 2 things that we did was there is a lot of regularization in this network, of course. And then lastly, we introduced a new form of data augmentation. Basically at training time, you can randomly merge together some census regions, and then you can create some, you can squeeze out a bit more data out of it.
Can I ask you, so
sure.
How do you feed this information in here? Is it just on the pixel level? You just have 1 neuron per pixel per channel?
I'm not sure if I understand the question. Like how this network operates?
Yeah, so what are the input neurons of the network? It seems it looks very simplistic.
So it's really an MLP, and it's a per pixel MLP.
So you don't use any, but it doesn't have so essentially it takes the pixel information and spits out an occupancy fraction.
Yes.
And but it doesn't use any information about translational
Yeah, there is no,
yeah,
there is no texture, no spatial correlation.
How do you deal with this? I mean, how do you make sure that if you shift your distance with the roadmap over by 1 pixel, that it doesn't lead to
I'm not sure if I understand correctly. You mean, what if one of the covariates is misaligned?
No, but just if you shift all the covariates, I mean, you have maps, right? So if you shift something, so I mean, your network doesn't guarantee, right, that if you rotate it, I mean, do you do a data augmentation, for instance, or what are you doing to ensure that you're not overtraining towards a specific, you know, let's say if you shift all your maps by 90 degrees, or
okay,
that you don't get a different object.
I mean, okay, now I understand. Yeah, I mean, there is no guarantee, and as I said, it's an ill-post setting. You can have different population maps. The only thing that we did is really just regularize it very hard. There was a lot of regularization in it, and then hope for the best. Run multiple random seeds, prove that your variability is still quite small. This is what you can do. But I mean,
I think so. I think if you rotate the image by 90 degrees, the prediction for each pixel will still be the same.
Yes. To this, it's invariant to rotations because it doesn't have.
So
it's still, but now the order of different. Right?
Yes, but so in here the model operates at pixel level.
Yeah.
So typically when you apply an MLP to an image for classification, at some point you will take you will flatten the representation of all the pixels, and so that's where you lose invariance. But here for each pixel,
I mean, here we have a sum operation, and sum is invariant to any ordering, right? So you don't have like
the left or the blue ones, right? The blue neurons, input neurons.
Yeah.
It's just the linear list, right? So you have to somehow linearize your 2D images, right?
So but that's just the features for that specific pixel.
Exactly.
Not for any other pixel in the image.
Oh, so the whole thing is pixel by pixel.
Yeah, exactly.
So you don't.
Yes.
Oh, you don't give it the whole map.
Exactly.
Yes.
Okay.
Thanks. So it's really perfect.
So if I ask you, when you use breeding count, so this is the including all the including scale.
Yes, it could also be industrial buildings.
Yeah, that's what I was thinking. So that exactly that's kind of narrow.
Yes, it's for the network, it's super misleading. Like in an ideal case, you would say, the network learns to identify those buildings and then put the occupancy rate to 0. I would wish I could say this, but we check the maps and it's not like this. So I think if we would have enough training data, we could learn to ignore those buildings. Yes. Yeah. All right. So one more thing I wanted to mention here. You notice that in this pipeline, basically, there are 2 different scales. There's the high resolution scale, like the covariates and the population map, and the census scale. And how you switch from one to the other is this sum operation. And I think this makes intuitively a lot of sense, that you can just sum over the pixel-wise predictions. But like for the methodology that I showed before, the random forest methodology, what they do is they sum the covariates first, and then they train the neural network. So I think this is the key difference between those 2 methodologies. So one nice thing about Pomelo is that there are 2 settings on how you can apply it. You can apply it either to the training site itself, then it's like a test time optimization method. You can basically improve the census data on this location, or you can train your method somewhere and then transfer it to an application site and then create maps there. So I just wanted to quickly show you what's the size of the data to give you a bit of an idea. For Tanzania, Zambia, and Mozambique, we kind of cherry pick those countries because they had nice test data, but at the end we only ended up using the course data of it. We just did this because we can better test it and validate it. But yeah, as you can see here, if you like big deep learning models, you will not have a lot of fun in population mapping because there are just only very few samples to train from. Yeah, so there are multiple different ways on how you can validate such a population method. The first one is that you validate within the same country. And the other one is that you validate in a neighboring country, basically transfer the model. And we saw that in both cases, we achieved quite good performance. And I also wanted to note that this random forest per region, the algorithm that I showed before, this is the algorithm that is used by WorldPop, so a quite famous provider of global population maps. And as you can see here, you get quite a lot of improvement out of it. Then the CNN basically it's also an implementation of ourselves. It's more or less the same guided super resolution technique, just that we use convolutions as well.
Was it useful to, because you could have used, if the network is very small, you could actually have used a random forest instead? Was it useful to replace the
the thing is that with the random forest, I can show you here. With the random forest, you would need to do inference with this sum operation as well, and then it gets computationally super heavy. So for each random split that you do, you would have to check the census and go back. So with just gradient descent backpropagation, it's a much more convenient method. I didn't check honestly, but yeah,
makes sense.
But I can imagine that the random forest would also have worked. Yeah. All right. Yeah. So there is also a third way of how you can validate your population maps, and this is basically just tested on a developed country and see how it performs. And this was then also done by one of our bachelor students. Here. Yeah, and we could basically prove that it also works on developed countries, just with one caveat that for big cities like Geneva and Zurich, where you have lots of high-rise buildings, you cannot really detect it because you have the building counts in it, but you don't have like information about how many stories are there. Yeah, but it's something we want to address in the future. I also have some qualitative results for you. So there are also other groups. Some of them are academic, like WorldPop, or non-academic, like Meta and Facebook, that work on population mapping. And we saw that with our maps, you just get much more detail out of it. And we think that such maps could enable much more, a whole new different set of applications for NGOs that operate in those countries. Yeah, so what are the limitations of this method? Basically, the first is really that we are super reliant on those covariates. A lot of those covariates, they are out of date and they are also not really reliable. I think, yeah, a significant part of the variables, they come from OpenStreetMaps, which is like very inhomogeneous, and yeah, sometimes the annotations, they are just missing for the current time frame. One other thing is also that I mentioned the Google Open buildings. It's very nice that we have those buildings, but using their building maps, it makes you really dependent on those large companies. And we also don't know if they ever plan to update this data set in the future. So it's a bit of a curse and a blessing. One other thing is that migration streams are super hard to model because yeah, the building counts, they don't always show also tents in it. That would be ideally quite nice. And then lastly, the fine-grained validation is still a problem, but yeah. So basically everything until now that I explained is like done work and also published. And now I want to show you a bit on what I'm doing now and how I want to follow up on this work. I will not go into all the technicalities since it's unpublished, but I will give you some sneak peek. So basically the idea is that we want to replace those context variables with satellite images and basically, yeah, extract some useful information out of it that we are not dependent on this anymore. And how the modality that we chose to do this was Sentinel-1 and Sentinel-2. So this is basically a radar sensor and a classical optical sensor, and both of them have a resolution of up to 10 meters. So 10 meters, I think, is like a bit at the border of what you need to detect population, but I think it's still useful because, as you can see, for example, here you see the urban structures a bit, and I think it's enough to infer where the population centers are, even though that you don't see the individual houses themselves. Also, one very nice advantage of these sensors is that they are open source. So if in the future some NGO wants to use the system, they don't have to pay for extra imagery. And the revisit time of those sensors or of those satellites are 5 to 14 days. So in theory, you can update your map very regular. Now the idea that we came up with was then basically to have input image some building extractor to extract some build-up score. In practice, we noticed that in such a building extractor, even in the developed world, and then do some adaptation. Okay. Yeah, we can adapt to developing countries. It works quite well. And so we use a frozen extractor and get a score out of it. And we do basically the same trick again as I showed you before. We estimate some sort of occupancy rate and multiply it, and then we get the population map. We use aggregated loss function again, and yeah, to train the whole thing end to end. Yeah, I can show you a bit of visual results. The nice thing is that a couple of months ago, some ground truth data in Kigali, Rwanda has been published, and this is on a 100-meter grid. So it's really seldom that you get such fine-grained data in developing countries. And yeah, so the first thing I did was just download the data and validate the maps. As you can see here, we get quite a lot better performance than WorldPop. And yeah, I wanted to mention here that these are the WorldPop maps that also don't use buildings as an input. If you use buildings as an input, you get a performance boost quite significantly. And this is basically shown here. So left is, again, without the buildings. And then on the right-hand side, you see the competitors' maps with buildings. And I would say that even though we don't use buildings, we can fare quite well with those maps that use high-resolution buildings. Yeah, so what's next for this project is that I also want to integrate some uncertainty measures into the map, basically do some Bayesian deep learning as well. And then finally, I want to increase the scope, maybe do an African-wide map, maybe even a global map. Yeah, so this is basically that was it for the population maps. It would be now a good time to ask a question before I switch gears to computer vision. Or you can also ask at the very end, that's fine. Okay, then I will go to guided depth super resolution. So basically, the setting here is, you saw some of the images before. The setting that we have here is we have an RGB plus D sensor, and this one records the RGB information, which is high resolution. We call it guide, and then the depth information, which is low resolution, and this is the source. And now we want to fuse those two modalities together to create a high resolution depth map. Yeah, now there are several different methodologies that you can use to fuse those modalities together. I tried to organize the things a bit into 3 different groups. So there are unlearned methods. Those are basically the classic methods, some inductive biases that you can use to solve this problem. And then there are also learned methods that are much, typically the learned methods are much more performant because they can use some data sets to learn the priors. And then the third category is hybrid methods. And for me, the definition of a hybrid method is that you can use it as an unlearned method and it works perfectly fine. But there should also be some mechanism where you can enable a deep learning backbone or the like to run it in a data-driven fashion. And then it should become more performant. And recently in the last 2 or 3 years, those hybrid methods became quite popular. And therefore, we also decided to develop our own hybrid method, which is called DADA, and it stands for Deep Anisotropic Diffusion and Adjustment. So this is the very coarse idea that we had. So basically, you take the guide and you extract some diffusion coefficients. And with those diffusion coefficients, you can enter a test time optimization loop and iteratively refine the initial source that you have. And now, as a quick disclaimer, whenever I talk about diffusion, I'm talking about the 80s style anisotropic diffusion and not the fancy new diffusion that was like super hyped in the last 1 or 2 years.
Can you maybe explain what it is, the 80s?
Yes, I will come to it in 1 or 2 slides.
Did you separate into 2 parts? I mean, the horizontal and the vertical diffusion. Do you have any reason for
I will explain. So basically, there are 3 different steps that you need to consider or that you need to understand in order to understand the whole framework. So the first is how you compute the diffusion coefficients. Basically, what you do is you treat the whole RGB map as a graph, and then for each of the neighboring pixels, so the north, south, east, west connection, you calculate a diffusion coefficient. So in practice, it's the Perona-Malik edge detection function, but you can just think about it as a classic edge detection function. It's just a bit formulated in a complicated way. So you get the horizontal and the vertical coefficients. You can, of course, also visualize it in one image, but I decided to separate it. Now you have the coefficients and you have an initial image, an initial guess of what your depth is. And then you can use the anisotropic diffusion to basically refine it. And there are 2 steps or 2 mechanisms that you need to understand in order to understand anisotropic diffusion. So the first one is you can see that there is a a depth gradient. And whenever there is a depth gradient, this encourages diffusion. So basically it smooths the whole thing out. And then the second one is the diffusion coefficient. And this one, you multiply it. And it tells you basically whenever there is a discontinuity in the diffusion map, you want to clip it to your output. So you want to hinder diffusion there. And what you end up is basically with this process that you see on the right, that the discontinuities get transferred, but you still keep the depth of your initial guess. Now, there is one problem with this methodology, and this is that the scale is basically lost. If you would now downsample this map again, you would not end up with the source, and this is kind of a problem because you lose the whole fidelity of your input, and therefore we crafted the adjustment step, which goes basically as follows. You start with your diffused depth, you downsample it, and then together with your source, you can obtain some adjustment ratio. And this adjustment ratio, you upsample, and then you can apply it patchwise to your input, and you obtain your final result. Now, the very nice property now, after you've done this, is that the source will always be identical to your downsampled map, which is nice.
I'm not sure I understood why you would resolution without the adjustments.
This one, yeah. The thing is that basically you don't have any guarantees on how your coefficients would look like. Assume that your coefficients would all be ones, so perfect transmission. You would end up with a completely homogeneous image here, right? Yeah. And then you downsample it and it's not the same again. So there is no guarantee for fidelity. Okay.
I mean, you kind of need close counters to ensure that you keep some high frequency information. You need to be sure that there are closed boundaries in your image.
Yeah, you don't need close boundaries. You can also have some diffusion coefficients that are something between 0 and 1. Mm-hmm. And this would then translate basically to some smooth boundaries that can also happen. But yeah, well, I'm not sure, does it answer your question? Or like,
I'm not sure I completely see the risk, like what do you need to...
I mean, it's not, I think it's also perfectly fine to do it without the adjustment step. And this is also what people used to do in the earlier days. Okay. It's just that you gain a lot of performance. Right. That is basically for free because you have all the information there. It's so close to the ground truth that I feel like you just need to use this information. And okay. Yeah, a lot of the guided super resolution methodologies, I would say they could gain just by using such an adjustment step. But like they use just the feed-forward methods, end-to-end trainable, and they don't have any guarantees that the output matches the source again. But it's just something that we came up with then.
Okay.
Yeah. Yeah.
Just from my understanding, could you explain? Sorry, what's P, what's N, what's N?
Oh, yeah.
For?
Yeah, sure. I only tried to do it a bit intuitively, but so P is basically your query pixel, and then you have the sum over the 4 neighborhood, the north, south, east, west. So the N is then the neighboring pixel. So for each, that means basically for each connected pixel, you exchange depth back and forth. Yeah.
Well, it's interesting because I was thinking in fluid dynamics, you use the heat equation.
Exactly.
It makes sense, but it's similar.
Yeah.
The diffusion coefficient, if you do the brute force approach, we call it a concept, just find it different, which is essentially what you have here. So you just discretize
Yes, yeah.
on a grid.
Mhm.
You have the graph is the same. You have always a component of the diffusion coefficient that is there is resolution depending. It's something so you put in a diffusion coefficient that is physical diffusion coefficient, but then on the grid you have an artificial diffusion coefficient that is inherent to the resolution. And there are ways to kind of limit that effect and so on. I guess you probably so here you also you have seen because I guess the resolution that can change when you have to detect an edge. If you have a resolution of your graph that is not high enough, always not able to really define the sharp edge. Unless you tune your diffusion coefficient with the resolution of your graph. Must be some tuning. So that's what I'm saying. If you have a very sharp edge, but your pixel resolution is not small enough, high enough, so the pixels are not small enough to where two different pixels on the size of the edge.
Yeah. But I mean, these diffusion coefficients, they come from the RGB image, which is high resolution, right?
Okay.
And the low resolution information is only in the source at the
So
bottom.
with the highest resolution diffusion.
Exactly.
I see.
Yes. Yeah.
Thanks.
Good.
And how did you solve the iterations? And did you use solving conditions?
We observed that it's basically always converging to some solution. So we ended up with having 8,000 iterations as a standard.
If you go further, then it goes like uniform.
No, it will not go to uniform distribution because we have the adjustment step. So in the worst case, you will have the source, which is also basically a good guarantee that in case everything goes wrong, you still end up with the source. Yes. Yeah. And it basically also answers a bit of Vivian's question, so it gives you a bit more certainty. Yes. Yeah. Yeah.
Also just like since from a physics background, right? You don't get any. You never get sharpening, right? It's always gets diffused out. So so what is the trick here to get a sharpening? It's to have this diffusion coefficient change from time to time, just in a bit of ways such that you get sharpening.
No, the diffusion coefficient is basically never changing. You just, I mean, there are, I think the classic formulation of anisotropic diffusion, it will change over time. We just noticed it doesn't make a difference and you save a lot of computation. So we just calculate it once and then it's static overall. So
what I'm confused about is how do you get sharp corners? So normal diffusion, right? You won't. You just got to swing it out more of this time.
Yeah. But I mean, we calculate it here from the RGB with an edge detection function, and then.
But where does this come into the equation? The equation itself is really just some discrete form.
Okay. Yeah, but
that's one.
But if it's almost 0 here, then you would I mean it's almost 0 here.
Yeah,
so
sorry,
the blue corners.
Okay,
oh yeah, sorry, it's very small here. It's almost 0 at the blue corners, so you have a discontinuity there. And then yes, of course, if you would just run it for infinity, it would eventually maybe converge to a homogeneous solution. But we have the adjustment step, which basically counteracts this moving. And so you will not end up with a homogeneous solution. You would end up maybe with a nearest neighbor interpolation instead. So it's like it's pushing in two directions, and what you end up in the end is something in between, which is a very nice looking solution. And this was something what we want to have. Yeah.
Say you have edge detection, vision, because it's very small. And so essentially what you do is that everything within those, so you're bounded by the edges, kind of smoothed out. That's what gives you very smooth levels inside these edges. And then of course, we have a nice approach.
Yeah, I think yeah, perfect.
The other question is, actually, I just,
yeah, sure.
would like to verify if it is, if I understand correctly. The thing is, after this formula, you update your edges and I mean the diffusion, the diffused image. But when did you apply this correction?
I will come to it. Yes, it's actually exactly the next slide that I wanted to show you. Yes. Yeah. So this is the whole overview at the end. So basically, you start at some initialization, for example, nearest neighbor by cubic. It doesn't really matter. And then you alternate between a diffusion and an adjustment step back and forth until you arrive at your desired solution. Yeah. So
you had 1,000 steps in diffusion, right? Diffusion
yeah, I will come to it. Yeah. So yeah, this is basically the whole setup. And you notice that until now, I did not talk about deep learning yet. So this whole thing, it can run without deep learning, just with the priors that I mentioned before. And now then, what we thought was then, yeah, so this is the RGB version. What we thought is, what if we take a deep learning feature extractor and then use this one instead? And we indeed managed to train such a deep feature extractor over 8,000 iterations. Which was not straightforward to do because you have to unroll the whole graph and then backpropagate. So there is one scheme that we came up with, and it's basically that you only take 1,000 iterations at a time and calculate gradients for them, and then you randomize the location of where you calculate the gradients. And we noticed that, of course, the more gradient steps you take, the better it gets. But at some point, you just get a diminishing return. So basically, your GPU memory scales linear, but yeah, at some point, the performance doesn't increase anymore. I wanted to show you also some the difference between what happens if you use the regular RGB coefficients versus what happens if you use the deep coefficients. Basically, with the RGB coefficients, you get a lot of noise into it, obviously, but also notably, here in the guide, there is like some periodic table, which is flat, but has textures. So the RGB coefficients, they get misled, very confused, very easily. But if you learn the whole problem in a data-driven way, then you can learn to ignore those cases. Yeah. Now, we tested the whole setup on various data sets and also various scales. So we tested it for up to an upsampling factor of 32, which is not like if you check the current literature, they usually only test it on times 16. And with our paper, we felt comfortable enough to also test it on 32. And we still observed a very good performance. So we also tested it on 3 different data sets. Yeah, basically Middlebury, NYU, and Dimmel. And then the unlearned version and the learned version. And without going into details about the numbers, the takeaway message is that in each case, we managed to outperform the competition. Some examples, yeah, some visual examples. You can see that the Middlebury dataset, this is a photogrammetric dataset, and it has super sharp corners for the ground truth. And then the other 2 datasets are captured with a time of flight sensor, so a bit of a noisy sensor. And we noticed that for the time of flight dataset, we think that our result is even a bit better than the ground truth. But it's very hard to prove. I will just leave it in the room like this.
It has the smoothing due to the RGB.
Yes, ours is move and has discontinuities, which is quite pleasing to the eye as well. Yes, but now there are also some limitations to our method. For example, in this sample, you can see this is a motorbike wheel, and you have some holes that are like trapped, and then you sometimes just don't manage to get those holes right, and this is still a thing that we think needs to be addressed in the future. But also, if you look at the competitors, none of them really manage to fill in this hole, except for one, which is the pixel-to-pixel transformation. Yeah, it comes from the supervision of Jan. It's a bit of, it's a few years old, but it's a really surprising algorithm. And so we think that in the future, we want to combine this algorithm with our algorithm. And yeah, we are quite, how do you say? We're quite confident that there is still something to be gained. And yet, the surprising thing about it is that this algorithm is an unlearned method. So maybe we can still spice in some deep learning and make it more performant. Yes, so this is the end of my talk. Those are the references that I used in the meantime. And those are my, this is my contact information if you have any question, and also the publications. Yeah, thank you a lot. Yeah.
I already asked questions.
Oh, that's fine.
Go ahead.
That's fine. Yeah.
Of course, it's the first time. Right. So, so if I understand correctly, your guided depth super resolution doesn't actually use depth data at the moment. It's really just images, right? Do you? Correct me if I'm wrong.
I mean, it's using the low resolution depth information as an input.
So you do use
yeah.
that, because I was confused,
Yes.
because your in principle your diffusion approach doesn't need anything, right? It just needs an image.
It needs an initial
Just
guess,
segmentation
right?
this way, right?
Yeah, it needs an initial guess of depth.
Yeah.
It doesn't need to be a super good guess, just some guess. It could be just some like low resolution pixels. It could be sparse depth, something like this. Yeah, but you need something.
This is for like cars or something like this.
Yes, for example, autonomous driving, but also like computational photography. If you have this portrait mode, if you try this, where it blurs out the background, for example, something like this. Yeah.
And mobile phones, right? The depth sensor is much lower than
yes, it's a very typical setting.
First papers, we got a lot of interest from Huawei, for example.
Yeah. So what does Apple have these things where you can change the focal lengths like afterwards? You take pictures and you and so do they do something like this?
Yeah, I'm
like
pretty sure they use.
I would know, I would be there.
I'm pretty sure they use some guided super resolution technique for it. Not sure what exactly they use. Yeah.
No.
Thanks.
Bad guys.
Yeah.
Do you have any other questions?
No, thanks.
Yeah, sure.
The first thing is, did you use only for, did you also use for some different types of modalities like SAR images or something like that with using this diffusion correction and the stuff? Yeah.
We are about to, we have lots of ideas on what we can do. Yeah, for example, pan sharpening would be a topic, the very first application that I showed. I think it would probably also work there. We currently also try to super resolve some vegetation maps. So basically vegetation height maps. Yes, we have lots of different ideas, but yeah, those are the things that are published yet.
Biodiversity maps would also be something.
Yes, of course, yeah.
Presence, absence, biodiversity data, so should satellite images.
And can you also go back to the framework and the big picture?
This
Yeah,
one.
this one.
Yeah.
Actually, I wonder if you try any, you already find some coefficients and you didn't change by time, right? I mean, in any time you use the same thing.
Yes, yeah.
If you use the intermediate information, like, I mean, this corrected output, let's say, and give for
feed it
another,
back here.
yeah, can you also make it in the loop, or did you try it?
We didn't try it, honestly, but yeah, I can assume that it might help, yes. Although I think the most information will still, like if you have this feature extractor, most of the information will come from the guide anyway. But it might help a bit, yeah. You can squeeze out a bit.
And your diffusion coefficients are in the range of 0 and 1, right?
Yes.
So did you also try minus, negative? Because it
so you
also
want to
shrinks into some places, which was your question, I guess.
Yeah, it's true. But I think as in physics, you want to consider a positive diffusion
Yeah,
coefficients.
yeah.
But
Otherwise,
So,
I mean, in mathematical sense, I mean, it should shrink.
I don't know what happens then. Whether
okay.
No, I tried it. So
Oh, you
I
did?
just, yeah,
what happens?
it shrinks. So that's the thing. Did you also try it, or?
I mean, it sounds a bit dangerous to have a heat source, or I didn't try it, but yeah. Yes.
Yeah, just a question, if I understood this adjustment step correctly. So what you do is you basically compute the low resolution source that you get from the, let's say, diffused image, and then you get a difference to the actual source, and then you basically add back those differences to recalculate them.
Yeah. So yeah, it's more or less what you say. So basically, the intuition behind it is just that you have your nearest neighbor interpolation grid, and then for each superpixel, you scale it up and down such that it matches the source again. Yeah, so it's a scaling operation. Does it make sense?
So the final guarantees that you always are like the low resolution is exactly the same.
Yes.
Every time you.
Exactly.
So there's a question that maybe you already implied the answer. If you have a source, so if the guide and the source are not so easy to map to each other, for example, is it how much you can still use the method? I mean,
They are not co-adjacent.
The alignment, yeah. Yeah, there is, it's an assumption that they are aligned indeed. Yeah. Honestly, we didn't test it, what would happen, but I wouldn't give you any guarantees now. Yeah.
But you could possibly add some additional loss, right? That sort of you shift something, but it would work less well. But what I can think of, have some astrophysics problem in mind.
Well, I was thinking about it. Now I was thinking about gas flow time. So something happens situation.
But I mean, there are some very specific guided super resolution techniques that consider this misalignment error. For example, there are some deformable kernel networks, they are called, which have like some adjustable convolutions. That like there are ways to deal with it. Yes. Yes. Yeah.
Sorry, this might be very obvious.
No worries.
How did you decide on which covariates to supply them?
For the population mapping project. So there are two parts for this answer. The first part is we just use the same covariates as WellPop used, just to make it super comparable. But the second answer is probably a lot of those covariates are not important. We did some feature importance analysis, and it showed that I think it was more than 50% of the covariates you can just confidently kill, and you still get quite a good performance out of it. Yeah, but yeah, like the most important variables. I think it was the night light variable and the distance to road. And yeah, obviously the building counts. Yes. Yeah. Yes. Yeah.
Question which I never understood when I read these kind of, maybe you can. So if you go back to this overview, this covered, yeah. So you have the ground truth thing.
Yeah.
And this source, is it just the downsampled ground truth place in the training?
Yeah, so for testing purposes, that's how we generated the source. Yeah, because we had a data set where the ground truth was given. Yeah. But yeah, in practice, you can also apply it to low resolutions data. Right. Yeah,
that was exactly my question. So your training data set has the guide and the image on the right, yes, in the same resolution. And yes, to train it, you downsample it to the source.
Yes.
Okay. So then my question is, if you look at a value in the source, then it is the average of the ground truth values. But yes, this is not, this can be different in the reality.
Yes, it could be that there is a shift. Yeah. So ideally,
if you have this low res image in reality, that is the value at this exact point. It's just that the spacing of values that you take.
Yeah, I think I know what you mean. Yeah, I mean, it depends on what your point spread function is, basically what's your mapping between ground truth and source. And then, yeah, you can basically exploit it a bit if you already know it. And then, for example, yeah, craft the adjustment step such that you have a strict adherence between ground truth and source, and that gains you performance. This is what you're going for?
It depends on the sensor, right, that you use for the depth mapping, for example. With time of flight, you have some laser pulse and you have some Gaussian drop, and it's at that point, it's what you need, right? So it's not the average of the whole pixel.
Yeah, so isn't it?
So that would be a Gaussian, it would be different way.
I mean, there are different sensors for it. For example, LiDAR sensor is a very small point, and then you have a sparse map, for example. That would be a different problem setting. I'm not sure if I really answered your question, but
maybe I have the wrong understanding.
We can also talk afterwards. Sure. Yeah.
I think we'll finish here. Thanks very much, Nando. That was very interesting. And yeah, let's go for lunch.
Thank you. We also have croissants and coffee outside.
Are they outside?
Yeah. So for some of the students, we will take essentially all the fruits and the croissants. So